You're doing well. Want to welcome everybody to the SCTE Chattahoochee chapter. This was our Q1 technical session, but we had to unfortunately reschedule due to technical difficulties. So now we've got it back on the session, on the schedule. Want to kick it off and run through the agenda, as well as just some basic housekeeping things before we get into the content for the day. So first, as far as the agenda is concerned, we will have first up Bill Clark with Vecima talking about all things vCMTS. That'll be followed by Jason Bisop of Cox Communications talking about Internet and Peering 101. And then we'll wrap up the day with cable network transformation in the SDN era with Thuy Nguyen from Intel. So appreciate all the speakers today. I look forward to hearing the content. And from a housekeeping perspective, as we go through the presenters today, for the folks on the line, if you have any questions, feel free to submit those in the questions section. We'll have somebody keeping an eye on those, so we'll either stop our presenters as they're presenting, or we'll hold all the questions to the end and get everything answered. If our folks can't answer it while they're on the session, we'll get you guys connected directly to have further conversations there. So please feel free at any time to engage and provide either any feedback or comments or questions that you might have during the session. So one of the reasons why we do these technical sessions, one is to help all of our folks, all of our members keep up with what's going on in the industry, what's going on with technology. The other thing that SCT offers to all of our members are various certification paths to help you all continue growing in your careers. As you go through these certifications, you get the training, you take the exams, you're able to gain badges and certifications for each of these classifications. You can put those in your email signature. They help you, solidify your expertise in certain areas, give you recognition for those skills and that extra work that you've done for the certifications, and then hopefully help you guys continue advancing through your career. And who doesn't like to earn more money? So if you have any questions at any time on any of the certification paths or how you go about that, please feel free to reach out to any of your SCTE Chattahoochee board members. You can also email certification@scte.org or go to scte.org/certification, and it'll give you all the information on the different paths. So please do take a look at that, and also know that on our board we have various proctors that can give those exams to you either in person or virtually. So really want to try to help our members continue growing and gaining as many certifications as possible in 2024. So let us know how we can help you. The other thing I wanted to mention is all of our technical sessions are free to SCTE members. There are various memberships available, but most of our biggest membership cohorts are the operators. So Comcast, Cox, Charter, various OEMs, and a lot of those, if you're not familiar, are part of the all access membership with SCTE. So through that, one, your membership is free. But you get free access to the technical sessions, your membership to SCTE, you get free certifications, as well as complimentary access to the Tech Expo that happens every year, amongst other things. So there's a lot of online learning sessions, etc., that you get access to. You get access to your membership, and your membership is automatically renewed every year, so long as you log in to your scte.org account. It will auto renew you. If you have any questions or challenges logging in, please feel free to reach out to me or membership@scte.org. I've gotten a couple that we've been able to get sorted out, but that's how you get your membership renewed. There's also various memberships available if you're not part of an all-access company. So I have the two links here for either a new membership or if you want to renew your membership. So those last for a year and you need to renew them annually. So we're happy to help at any point with that. If there are any companies that want to do a membership drive, want to help your members get renewed, we're happy to set up, an appointment or a time to help support your people with that.
At Vecima, working in the Video and Broadband Solutions business unit. He has been working for vendors in pre-sales engineering for 30+ years, selling to both MSO and telco service providers. Ultimately, engineering systems using 56K dial-up modems to broadband access and all the equipment in between. So Bill's been around a while in the industry. So Bill, you ready?
Thank you. So if I had hair left, it would be gray, but I don't have hair left. So this is about, I predate DOCSIS. So what we're going to talk about today, and thanks for having me, Krista and Jason. I think I did one a couple of years ago where I actually had to narrate it, but this is going to be everything that you need to know generically about virtual CMTS. So I'm not going to go into any specifics on, solutions that anyone has. We're going to talk about what it means and things like that. So
I'll start to interrupt you. Can you swap your displays up top?
Which one? Oh, I got the wrong one. How do I do that? There should be a button, right?
At the very top, I think you just hit swap displays. We should be good. Top left.
Top. Oh, here.
There we
go. All right, good. I thought well, you know what? It picked the one that it wanted to pick. It didn't pick the one I wanted to pick. So, but that's okay. All right. Here's what we're going to talk about. I'm going to sort of give you a definition of virtual CMTS and talk about some key features like scaling resources and things like that. We'll go over the benefits, about what a virtual CMTS does and how that works, and then we'll talk about some deployment strategies of what that would be, for a virtual CMTS. So, getting into it, just a little background. Today everybody knows how the cable broadband system looks, going back from legacy broadband, until where we are today. Things are evolving. So, if you go back, to pre-DOCSIS and telco return systems, all the way up to now, we have DOCSIS 3.1, remote PHY, and remote MAC-PHY, things of that nature. Worldwide demand is still constant for broadband, but enhanced services are being asked for. And now what we're looking at now is we've got a user base that has changed somewhat because we have work from home hybrid people. So there used to be a time where you would know or have a very good idea about what the throughput needs were during the day versus at night. And then the streaming media started happening and, all of those peering applications. But now you don't know if a worker is going to be at home needing bandwidth or is going to be in the office. So things are changing, things are evolving with the network. So that's the perspective from the user. From a service provider, there's also a need and a real need to be prepared for that change in what the users look like, and also competitive pressures from fiber, wireless, things like that, to kind of get your system prepared for that. And then during the same period of technical evolution, there's a focus on the next version of DOCSIS, how that's going to look, and what we're going to do with that. So today we're discussing the rise of the virtual CMTS. The challenge at hand today consists of dealing with changing network congestion patterns as we deal with those hybrid workers and be able to have bandwidth and throughput when you need it at any particular time. So that's where we're going to be right here, talking about the virtual CMTS sitting in the hub or data center, and where that kind of plays out. So the simple definition of your your virtual CMTS is sort of well, it's software based. So the challenge created by all of these end users moving around has brought about the transformative change in how we view that CMTS. A virtualized CCAP not only represents the change in how we provide that and manage those users, but also how we can control our broadband infrastructure. In basic terms, the virtual CMTS is a software-based CCAP running on COTS servers in a hub or in a data center. However, the details suggest that we are far more, there's far more going on as we take the control plane and the data plane and virtualize it. So it's a lot more of a detailed definition as opposed to, it's a software-based CMTS. What virtualization brings is flexibility, scalability, some cost savings, and it also sets up the CMTS to now be software defined, which I think you'll hear something later in the day about that, and set up some of the network function virtualization technologies that are emerging in cable broadband networks. Oh gosh, I can't get these. I hope you guys don't see this. Get this off.
Yeah, we do. Do you want to switch over, maybe share your other screen instead?
Yeah. Or what I could do, let me do this. What I could do, if I can find my mouse again, I could make one of my other screens the main screen. There we go. Hopefully it won't show up again. All right. So did I lose where I was? Yeah, I probably jumped ahead. Okay. So, how do you get to this virtualized CMTS? So, everybody's heard the whole concept of cloud native and, what that means. Cloud native is the process to streamline software development, but also deployment and operation. So from the vendor's perspective, cloud native means some things and how the applications are looking. From the MSO's perspective, it's how you deploy your virtual CMTS, and that's going to be via containers. So the containerization of all of the processes that are within the big iron is where you get the meat of what the virtual CMTS is, and it's going to provide a consistent environment for your virtual CMTS functions to run across the cable network. And as you'll see as I get into this, it'll be the case of putting bandwidth where you need it, when you need it. So dynamic scaling is the way to automatically adjust for the number of resources based on the capacity demands and the system load when that happens. So in a traditional CCAP deployment, you have specialized hardware, which we call the big iron. And that's going to have your data modulation, demodulation, all the routing for your data traffic. All of those functions have to be virtualized. So the virtual CMTS is going to replace this hardware and its functions with software containers running on standard, x86 servers, with some caveats depending on what type of NIC cards and hardware acceleration you have within those servers. And that's going to be in a private, public, or even a hybrid cloud. And it's going to make it elastic, which you'll hear a lot, meaning that it can be whatever you need it to be when you need it to be. And it's going to be more of a dynamic approach to getting those services out there. So, as I break down the components of a virtual CMTS, if you look at the cloud native part, the definition is, pretty generically, per Wikipedia, It's the approach to software development that utilizes cloud computing. And you can read this, but built on scalable applications in modern dynamic environments. To put it into perspective as it relates to cable broadband system, it's developing a virtualized CMTS that organizes and orchestrates DAA networks that are built with components from multiple vendors, and you have those components can be your PTP master clock, your SYN switches, DHCP. So all of that gets virtualized into containers and deployed in a scalable fashion via microservices throughout your network's footprint. The key concept of the virtual CMTS is that it should be interoperable with common third-party components, which enables you to be more flexible and get the best of breed of products and things like that. The cloud native approach with the microservices, it creates smaller applications that can be deployed. They're developed in a way that they can scale independently when and where they're needed. The applications and their dependencies, are packaged into lightweight containers that run, consistently in different environments in the cable system. And you'll hear a lot about the containerization of these functions. These containers are managed and orchestrated dynamically, by industry standard platforms like Kubernetes, Nomad, Docker, to put those lightweight containers where you need them, when you need them, and they can be replaced. And it's going to, quickly, and it's going to ensure a consistent and reliable service. Now, there's a number of, DevOps practices that are out there. They're kind of out of scope for what we're talking about right now. They function as a way to get things in a cloud native approach for the CMTS. As it relates to what you guys are doing, it's going to allow you to do what I like to call adding capacity when and where you need it versus adding capacity until you need it. This agility is going to make your networks easier to deploy, and it's going to save you resources. So you're not sort of overburdening or overusing resources in a particular area because you feel the growth coming, so you have to put in a new CMTS or something like that. With the virtualized CMTS, you can spin up instances as needed when needed. And I'm not really looking at the questions. Feel free to kind of jump in and ask questions as I go on. I do tend to talk a lot and fast.
Hey, Bill, there aren't any questions yet, so we'll let you know if there are any for sure.
Okay, yeah, because I'm not really looking over at that part. So, where are we? We know the elements of the current CMTS. You've got the chassis, you've got all of the RF, which now is out in the node via remote PHY. But then there's the other processing, the protocol processing, the MAC layer, routing, switching. All of the things you see here and more are the elements that get containerized. And what that's going to do is it's going to allow you to to isolate functions where they're needed. Containers can take whatever operating system level and work within that that concept, and they're more portable because you can take a container and you can move it anywhere in your footprint. And as I'll talk later, from a deployment strategy, you can actually have the control function be in a data center, but you can distribute the data plane out into your plant, and the containers will just be there and they'll be controlled in one location. So the way things get implemented is changing for the good with virtualization. And it's going to make it more efficient for you to deploy your services. It certainly will make it more flexible. And then the orchestration around that using Kubernetes and Doxes, things like that, and Docker is going to allow you to do everything in an automated fashion. Okay. And I don't know how we're doing on time. Yeah, okay, I got my watch here. All right, so let's talk about dynamic scaling. Because the dynamic scaling and all the resource allocation is going to let you adapt quickly to evolving network conditions. It's going to allow you to optimize the performance of your system and deliver your high quality bandwidth services to your subscribers efficiently. So from a dynamic scaling standpoint, you can adjust capacity of the cable broadband infrastructure based on changing demands. So if you look at it in real time, you can say, well, what's my peak usage rate? Which at one point, I think we all kind of knew what the peak was going to be. But now that we have streamers and now that we have hybrid workers, that has changed a little bit. So now dynamically, the system can adjust to that based on, how you deploy your containers in your system. And also, from a resource allocation mode, you're not going to stress your big iron CMTS anymore, because with a virtualized system, it's going to be able to control the CPU and memory allocation, and it's going to take that bandwidth and using whatever complex traffic shaping, and it's going to do all of that automatically. And from an elastic standpoint, it's going to take those resources for provisioning. It's going to allow you to scale resources up and down in response to changes. And because it's orchestrated automatically, it's going to do that without pretty much without a hiccup. Okay, so in a real sense, you could see perhaps the virtual CMTS as reducing hardware costs. So, one of the things I like to talk to people about also when they're talking about cloud, infrastructures and whatnot, every software package runs on somebody's hardware somewhere, whether it's in the cloud or whatnot. So when you take away the appliance part, and you move the big iron out of the the data center or out of the hub, you're going to receive some responses back for costs for power, cooling, and things like that. So there's an operational expense reduction in moving to a cloud-based system. But keep in mind that there are going to be costs somewhere for hardware. It's just that how that hardware is going to be worked into your system is really a function of whether you're going to distribute your system or have a centralized system. But overall, virtualization drives the significant cost savings, in terms of reducing the hardware for the appliance, and you're kind of shifting that to different parts of your network. These cost efficiencies contribute to the improved profitability and competitiveness of cable operators as they sort of invest more wisely into platforms that you're probably already running in your data center, because you have virtual machines running on other applications that you have within your system. And then being able to centrally manage your CMTS, because you do maybe have your control plane in one location, is going to give you some cost savings as well. And as you further define your configuration, you're going to be more agile, and it's going to enable you to respond quickly to changes in your network. So if you look at it in the sense of from an outside plant, you've got your nodes out there, but by and large, the control is going to be in a data center somewhere, with maybe virtually distributed management planes somewhere, if that's your model, or it'll be collapsed back into one location. Okay, so resources, when you need it and where you need it. So, I mean, I talked about this a little bit, you know, whether it's horizontal scaling or, you know, the elastic scaling, the whole idea behind this part of it that's really has a lot of people excited is not, you kind of move away from the build it and they will come scenario into something more of a build it when you need it scenario. So this aspect of the virtual CMTS has, you know, everybody excited, especially the people for service delivery, because now they're able to do real-time adjustments to get the bandwidth where it needs to be, and it's going to be dynamically adjusted. So there's no stranded compute anymore by, you know, taking moving into a new area or having to increase throughput. So you're going out and you're investing in a large CCAP that's going to be in a new area, but you know, perhaps the need isn't quite there yet, and you're waiting for it to grow. And then, you know, things change or, you know, demographics change, and now you've got a large investment that's being underutilized. With virtual CMTS, that's not going to happen because you will spin up containers as needed dynamically. So efficient resource management. Ultimately, we're all looking for that superior user experience. You know, fewer calls. You know, how that happens is by allowing you to have better management of your system, to have a way of providing these services automatically and dynamically, to scale it, you know, based on, you know, where the customers are moving to. You know, do they work at home Monday, Tuesday, but you know, Wednesday, Thursday they're in the office, and then, you know, back at home Friday. Virtual CMTS is going to handle that because it's going to find where those bandwidth changes are needed, and it's going to be orchestrated to change at will. So also with the virtual CMTS, geographic redundancy and high availability is in play because, you know, once again, we're just talking software running on servers somewhere in the network. So that's going to allow you to have a diverse path to your control planes and even your data planes based on where those VMs reside. So efficient resource utilization. You know, countless amount of times you can look at a system and one system is just running 100%, or well, not 100%, is running flat out, and then other systems aren't really running at all. And so you're looking at it in terms of, well, we're not using our resources wisely. Virtual CMTS will take care of that because it's going to put the resources where it needs to be. So from an operational efficiency and cost savings standpoint, you're taking what is the meat and potatoes of your DOCSIS system, and you're managing it a heck of a lot more efficiently to do the jobs that you need to do. So as you turn up new customers are moving, you're responding to them at a much better pace than you were before. So, oops, I went the wrong way. So we'll talk a little bit about the deployment strategies, centralized versus distributed, and even hybrid. So as you move into a centralized deployment, you've got much simplified management because everything's right there. Your scalability is going to be good, your cost savings. You know, there are some network latency issues that may have to consider when you go to a centralized deployment strategy, because everything is coming out of one location, and then that gives you that single point of failure. So, you know, depending on the size of your operations, how many homes pass, centralized may be the thing for you. If not, you know, if you're larger or you're more spread out, then you can get the advantages of being distributed, where you put your virtual CMTS out in regional locations closer to the subscribers. Going to get a little bit better latency. Your high availability is going to be better because you can actually tie virtual CMTSs, you know, in a geodiverse way. And scalability is always going to be there because that's the underlying tenet of virtual CMTS. Now, it will be a little bit more complex to manage, and you'll have a little bit more infrastructure costs as you put, you know, servers out into, you know, your regional locations. So what that means then, if you look at the hybrid approach, it kind of overcomes a little bit more of the latency, but it also is going to provide you the benefit of having centralized management. It's going to reduce traffic across your network, and it's going to, you know, able to take your data planning off to the local regional location. So it is probably the best of both worlds, where you centralize the control plane and distribute the data plane. So, looking at the architecture, and now, Chris, this is probably the last slide, and we can have question and answer.
Hey, Bill, I do have a question on your last slide.
Yeah.
I'm curious, from your perspective, do you think most operators are going distributed, centralized, hybrid? What are you expecting to see?
So, and I was just thinking about this on the way in, because I was kind of anticipating this question. Every operator kind of does things the same way, because we're talking about a very spec-driven, you know, broadband offering. But in another sense, every operator is a snowflake. So it really depends on the size. It depends on how your system looks already, where you have your resources, how many data centers you have, things like that. I would anticipate an operator of size to want to do a hybrid type of deployment. And, you know, that control plane is not necessarily a singular place. You could have multiple data centers around your footprint that you can have a control plane in, but you're still always going to have way more regional locations that you have to service. So if you're smaller, centralized may be the way to go. I can't really give you a number of homes passed or things like that, but I foresee a lot more hybrid than just centralized or just distributed. Does that answer your question there?
Yep, thanks.
Okay. So at the top, you see the containers, and as I mentioned, it's all of the functions outside of the Thuy functions, which are in the node, that gets containerized. So how the virtual CMTS you are going to deploy does this is a function of how it was developed by, you know, whatever vendor you're choosing. But this is the meat and potatoes of how it gets done, taking these microservice containers and delivering them, you know, where they're needed, when they're needed. So the next evolution of this, when DOCSIS 4.0 comes along, is going to be somewhat of a seamless deployment, because it'll just, all the functions that are needed will just get containerized. So as Cable Labs changes some of their, or enhances some of their specs, you know, that's going to go into the DOCSIS protocol, you know, containers, and, you know, and then those will be distributed throughout. So the fact that these containers are lightweight, they have their own operating system, it makes it so much easier for things to be scaled, so much easier for things to be deployed, because they're taking containers and they're just spinning them up as needed. And another one of the aspects of these containers is that if it's not being used, it's called immutable infrastructure. They're going to be taken down, and just done away with. So you're not going to have containers sitting out there not being used and then trying to reuse them. They're so easy and lightweight, you just spin them up again.
Bill, also a question came through that says, are there any new capabilities to manage ingress?
So once again, that would just be a container. So ingress, like I'm assuming sweep, OUDP, all of these are just DOCSIS protocol processing things. Everything is a container. And it's all built into, today into your CCAP. And some of these functions you don't really notice because it's just part of the way it is. They are being taken out and containerized and will be spun up as needed. So I think it's the very good thing about it is things that come up that are new, you don't have to go and reinvent the whole wheel. You're just adding more spokes, if that makes sense. So one of the things I do want to talk about, I have down here the COTS hardware. It is COTS hardware, but potentially there could be some caveats. If you look at any server platform by any vendor, they generally will bake in some level of hardware. It's not necessarily proprietary, but it's some way to accelerate their hardware. And they may tie, say, a NIC card to it that you have to use. But by and large, the compute for virtual CMTS is COTS. The host OS, I have here generic. Some systems will have generic, Linux OS. Some will have some that are very specific to the virtual CMTS, or some will maybe allow the MSO to have their own OS. So from that standpoint, it's very easy to deploy. You're just picking the OS that you need. And then the orchestrators are really on the lines of what the particular vendor wants to use. There are so many different orchestration platforms out there. Most vendors tend to stick to something that's open, an open system, but there are those, Kubernetes, DOCSIS, they're all out there, Nomad. It's going to allow the virtual CMTS to function with orchestration that basically the system is spinning up containers as needed. So it is the wave of the future for remote PHY, because as you can probably tell, the big irons are going away. Not necessarily the companies, even though we know what's going on with some of that, but definitely the virtual CCAP. Any other questions? Did I go too fast?
I don't think so.
I have one more question for you, Bill. So,
Sure.
So most of the big operators, Comcast, Charter, Cox, are doing remote PHY. But we do know that some in the industry are still doing remote MAC-PHY, or still looking that direction. Do you have any perspective on, I guess, R-PHY versus RMAC-PHY in the industry? Or do you think more companies are going to move to R-PHY, or what is your perspective?
So, without getting into a sales pitch here, there is a definite need for MAC-PHY for those providers who are not of size, and you can get into tier 2, tier 3, and some people even say tier 4. As a sales engineer, I talk to customers constantly in the small provider space who are still in DOCSIS 3.0 mode and looking to move, but they have 25 node, maybe 50 nodes. They haven't purchased a CCAP, or they do have a CCAP, and now they have, well, do I extend that? Do I buy new licenses? So we're seeing a tremendous need for MAC-PHY for those providers that are in that space. From a tier 2 space, we still see interest from some of those providers as well. So there's a definite need for MAC-PHY around the globe, because it's not just a US thing, and we're seeing a lot of that. And outside of, and I can tell you guys, I support Cox. Outside of that, most of my time is spent with MAC-PHY for the smaller providers. So it's still a definite thing, and will be for quite some time.
Yeah. Cool. Thanks.
Any other questions anywhere? Let's see here. Okay. So I appreciate your time. I always like talking to people. I talk a lot. Even though I can't tell who's on, I'm sure I've seen a number of you, because I generally will be at the first hole at Stone Mountain on one of the 2 courses. So, and I will be heckling people again at the next golf event before they kick off.
Well, Bill, I would like to thank you. I'll send you your gift card on the side here. You've given me a really nice segue. If you're good and ready to wrap, I would like to launch a poll to the attendees really quick to try to gather some feedback for our vendor and golf day real quick, if that works for you. And Jason, I know you're next up. So I'm going to launch this poll real quick. If those on the line could, it's a very quick one, but would love your feedback as we try to plan for our vendor day and golf event this year.
Okay.
Why is it? Oh, here we go.
Ooh. I know what month I would pick.
Well, send me an email with your feedback, Bill, as well. Obviously,
Okay.
I think because you're a panelist, it says you can't vote, but
Right.
we want yours as well. Give it another 30 seconds or so. Give everybody time to respond. Looks like October is the front runner right now. 71% for October, 29% for November.
I don't have to send you my email then. I was just October also. As someone who's been sitting at the hole when it was cold versus when it was not cold, I will go for not cold.
I hear you.
That's what I was thinking too. Swinging a golf club when it's cold is painful.
Yeah.
All right. Well, I'm going to close the poll out. Thank you to everybody who responded. We got a 63% response rate. So thank you to folks for that. Very helpful. All right, Jason, I am going to turn it over to you. Jason is going to be our next presenter, and he is going to be speaking on the Internet and Peering 101.
And can I just hang out for a while, Kristen?
Of course, absolutely.
Yeah. All right, can everyone see my screen?
You can.
All right, thanks, Krista. So hi, I'm Jason Bisop. I lead the core design engineering team at Cox Communications. So my team is responsible for the architecture and design for the core routing and long-haul DWDM networks that make up Cox's national backbone, as well as the metro routing and DWDM networks in each of our market locations. So I did do this training session in early 2023, but figured it would be a good refresher to go over again. I'm going to cover some topics that I would say most don't have much visibility to, so hopefully this will connect some dots for people. And the more questions, the better. And you can always reach out after the training if you do have follow-up questions. So the internet is a network of networks, or more specifically, it's a collection of autonomous systems. So an autonomous system, or AS for short, is a large network or group of networks that are managed and controlled by a single entity or organization. So I just have a couple examples on here. So for example, at Cox, our autonomous system, or AS, is 22773. So to the internet, that's our identifier. So these numbers are unique to each company. And I'm also showing on here Akamai, Netflix, Comcast. So we're all considered tier 2 networks from an internet standpoint. I know that might be a little confusing because you hear tier 1, tier 2 when you hear of these companies and how many customers they have, how large their network is. These tier classifications they kind of differ with the context. So from strictly an internet standpoint, we are all tier 2 networks, which I will explain on a later slide. So at the top, I also have level 3 and Aurelian. So they're considered tier 1 internet providers because they do have global internet reachability. So another thing to note that the network size is really irrelevant. So an AS or an autonomous system could be a network as small as 100 routers or servers or 100,000. To the rest of the internet, that network is a single entity or AS. It is possible for companies to have multiple ASs based on how they have segmented their networks. For example, Akamai, who is a content delivery network, they use one AS to get content onto their servers, and then they use a different AS to distribute that content to end customers. So this one I'm showing here, this 20940, this is their content delivery network, the AS they use for that. They use a different AS to get the content to their network from wherever they're getting it from. So as you can see here also, Cox and Comcast both sell internet connectivity to other customers or other companies. So I just have here just X's. I mean, this could be any number here, and this quantity of customers, I mean, could be in the hundreds, could be in the thousands. I'm going to show you some views a little later. There's some ways that you can actually see who these downstream customers are and also visualize some of that. So I'll show you that a little bit later. So all of us, operators, content delivery networks, we all must connect to tier 1 providers in order to reach the global internet. So we establish those links and we connect to people like Level 3 or Lumen, Aurelian, GTT, AT&T, Cogent, or some of the other ones out there. So once those connections are in place, we can reach the rest of the internet. But there is a downside. Those connections to those transit providers aren't free. So we do have to pay for anything that traverses those links. And this is what's known as IP transit, or just simply transit. So we have to pay for any traffic, any packets that go across these. There is a fee that's negotiated between the company and that transit provider. So those connections are usually billed at a certain rate per megabit. Although the cost per meg has decreased drastically over the last couple decades, the amount of traffic on the internet has also grown at enormous rates, especially once streaming video services like Netflix started. So companies do everything they can to reduce these IP transit expenses. So, you might wonder, so what is the best way to reduce that expense? And the answer would be to actually connect these networks directly together and not go through a transit provider. So here, for example, I'm showing a connection from Cox to Netflix. So this is what is known as direct peering. Any Netflix streams in this example to Cox customers go directly between our networks and not through any of these tier ones. And we also don't charge each other for that connectivity. And I'll get into that more on the next slide. So this is more like what the internet looks like today. So these dashed lines are all direct peering between tier 2 providers. So any traffic or content exchanged between our networks doesn't have to go through tier 1, which means it's free. The main goal we all have is to minimize those IP transit expenses. So most large companies are roughly 90% of their traffic is coming through these direct peering relationships, which is free. And then the remaining 10% of those are IP transit. And one last thing on this slide. So I am showing a single line between these companies, but in reality, these connections could take place, in 5, 10, 15 or more locations across the country. So there are data centers spread out really all over the world where companies like these connect to each other. I'm going to show something a little later too that'll help visualize that. All right, so let's look a little closer at the differences between that IP transit and the direct peering. So the primary reason for peering is to improve the customer experience, so we can connect directly to content providers and also obviously we want to reduce the overall cost of that traffic. So we want to reduce our IP transit expenses. And when I say content providers, I'm referring to gaming, streaming video such as Netflix or Amazon Prime, social media. One thing that we've noticed in our network and others have as well is TikTok, or company is known as ByteDance. The amount of traffic going to TikTok is pretty crazy nowadays. It's really interesting when you're watching some of this stuff at this more I would say company-wide perspective, and seeing what type of traffic exists in the network. Is it just web browsing? Is it streaming video? But also just seeing what companies pop up, or which ones maybe aren't popular anymore and start dying off. It's really interesting watching that stuff. So on the left side, in this IP transit scenario, so content comes into and out of your network either through a transit provider. Hold on, lost my book for a second. So this type of scenario, I would say, exists for mostly smaller content providers. One example I like to use is, let's just say you have a customer that's browsing to some website that's hosted in Brazil or South America. More than likely, especially with a company that only has a presence in North America, more than likely we don't connect or do direct peering with that company, with whoever's hosting that site. So traffic like that will come through a transit provider. like these three I have listed here. But for any of the larger ones, like Netflix, once it gets up to a large volume of traffic, that's when it makes sense. One of the companies will reach out to the other. Hey, we want to establish this direct peering with you. Are you good with that? These are the locations we're in, and then we'll actually do that direct peering or that settlement-free peering. So couple of the main benefits, like I said, of direct peering, it is an improved customer experience because this is a more direct path between networks. We don't have this, call it the middleman or the IP transit provider in between. So this literally goes directly from, let's say, an Amazon router to a Comcast router or a Spectrum router. They are directly connected to each other physically. Like I said, this cuts out the middleman, and then probably the biggest benefit is it does reduce your IP transit expense. So this type of peering is known as settlement free. These companies don't charge each other because really this is mutually beneficial to have these connections directly between. So there's no expense here. So I've mainly been talking about direct peering, otherwise known as private peering, but there are some other types here as well. So first to recap real quick, so private peering is settlement free, meaning we don't charge each other. It's also referred to as private network interconnect or PNI, you may hear. For that connectivity, there are also physical cables that need to be ran inside a data center, which the data center companies charge monthly recurring fees for. And I'm also going to show that on an upcoming slide as well. So when companies establish a PNI relationship, they're usually doing it in 3 or 4 sites or more across the country. They'll usually come to an agreement where one company pays for that interconnect expense at site 1, the other company might pay at site 2, then the first company pays at site 3, just to equally distribute that operational expense of having those cross connects. So the next type of peering is known as public peering. This is sometimes referred to as an internet exchange or IX. So data center companies will build a networking environment in their facility and encourage companies to establish a physical presence there with the hopes that the companies will all connect to each other. You may have heard of this referred to as fabric peering. It's another way. There's a lot of different names that kind of describe this type of peering relationship. So these connections are fast and easy to set up. Although you do have to pay for the physical link to the IX, any peering that you establish with other companies will be free. So basically you get that physical link ran once, whether you're peering with one company or 50, you have the expense of that physical link, but after that, once that link is established, then it's just configuration, basically router configuration to set up additional peers there. These peering environments are really ideal for a large number of small interconnections with small volumes of traffic. Like I mentioned, a website hosted in Brazil, whatever company that might be, maybe they do establish a presence in North America, and companies that connect to these internet exchanges can get directly between them. For companies that have large volumes of traffic like MSOs, it makes more sense to directly peer with content companies versus going through public peering. Now, the last type, just kind of generically calling it paid peering. This is really used to describe an operator like, Comcast, Cox Charter. It can be used to describe when they offer transit services for a different company. So on that first one, I showed customers hanging off of those networks. Those are paid peering. So those companies actually pay the operator for that connection, and then that operator because of their connectivity to transit providers and all the peering relationships they have, they can give that company access to the global internet. And then they do charge a fee for that. Whoops. So I've mentioned tier 1, tier 2 a couple times. I'm sure you've heard those. Like I said, in case you weren't aware, those are informal definitions. So there is no governing body or official organization that classifies a company as a tier 1, tier 2, or tier 3. How a company and its customers reach the global internet is really what dictates how that company is classified. So a tier 1 is a network which does not purchase transit from any other network, and therefore they peer with every other tier 1 network to maintain global reachability. So these are the companies like Level 3, NTT, AT&T, Cogent, Aurelion. They don't charge each other for this connection, and they do have these physical links established all over the globe. They all have global reachability, and there's only about 10 to 12 networks that really fall into this category as a tier 1. So a tier 2 network is a network which has some level of direct peering, but still must purchase full transit to reach some portion of the internet. And they also sell transit to customers as well, typically for cheaper than what the tier 1s charge. So like I'd mentioned, some examples of tier 2s are the MSOs like Cox, Comcast, and Charter. Most content providers also fall into this category as well. So that would include companies like Amazon, Netflix, Google, Akamai, and the other CDN providers. Then a tier 3 is a stub network, typically without any transit customers. So there aren't any other companies hanging off, and also without any peering relationships. So these tier 3s don't typically connect to any other tier 3s. These tier 3 companies, though, these do make up the vast majority of the autonomous systems or the ASs on the internet. So like I said, there's about a dozen tier 1s. I don't know the number, but let's say there's 500 tier 2s. The other, 50,000 or more ASs out there are these tier 3 networks. So where do these peering relationship takes place? So there are numerous large data center companies in the US, as well as the world, but just focus on the US here. But two of the more well-known ones that I'm going to highlight are Equinix and Digital Realty. There are others like, you may have heard CoreSite, EdgeConneX is another one. There used to be one called ViaWest, which is pretty big, but they got bought by someone else. So Equinix and Digital Realty provide the infrastructure for companies to interconnect. These data centers are really large. The typical ones are 100 to 150,000 square feet or more. And these two companies, Equinix and Digital Realty, they actually own over 500 data centers worldwide, and they have thousands of customers. I mean, these are very large companies. So companies lease racks within these facilities. So in a facility with a small footprint, you may only have 8 or 10 racks of equipment. But in a large facility in a dense part of the US, let's say Los Angeles, New York, depending on where your customers are, you might have, or an operator might have 40 or more racks of equipment in here. So it really depends on the density, what markets you're serving from that location that dictate how large this deployment is. So not only do the MSOs lease rack space in these facilities, but the content providers and other service providers also lease space and power in those same facilities. So over here I have, a bunch of company logos just showing as an example. They may only have 1 or 2 racks. Maybe it's some really small routers they have. Maybe they have routers and servers. I mean, it really doesn't matter what they have, but they lease space there as well. So these data centers have something called a meet me room, or sometimes just shortened as MMR. That is the room where all the actual fibers and connections are ran between these companies, between the equipment from each company. I'm going to go into more detail of that on the next slide. In some of the larger facilities, it's possible to directly peer with 30, 40, 50 companies. Here I'm showing roughly 10. There could be 100 different companies that have a presence in this data center, a physical presence here. It may not make sense to connect to them all. Maybe you just connect to the ones that are generating the largest volume of traffic on your network. Like I had said before, there is an expense for having these physical connections ran. Companies do pay a monthly fee for that, and it's in the hundreds of dollars. I mean, it could be $200, $300, $400 per fiber per month. So, it's a pretty significant expense. So obviously companies have some pretty strict policies that kind of dictate who they're going to peer with and actually incur that expense. So one other thing I wanted to mention is how physical work gets done at these locations. It really isn't feasible for companies to send employees to the location every time they need to do work. So let's just say, Cox wants to connect to Google. We don't send an employee to this data center, wherever it is in Google. These data centers actually have people on site that you can pay a fee to and have them complete work for you. So that's actually known as smart hands. Most of the work that companies have done in these facilities are completed by smart hands. If it's a significant deployment, or maybe a company is replacing all their routers or their optical gear transport, more than likely they're going to send one of their employees out to go do that work, because it is, it's complex, and having to describe all the work that needs to get done to someone else would be pretty difficult. So there are times companies send people to these locations, but typically for most of the work that gets done, they are completed by those smart hands. So let's take a closer look back to the meet me room and then go over how we actually connect to peers. So every company that deploys equipment in the data center also has patch panels that connect back to a common location. So now you have a room full of patch panels from all the different companies in the facility. In order to request a link between patch panels, a letter of authorization, or LOA, is needed. Once that paperwork is filled out and on file, then the facility staff or the smart hands will run the fiber jumper between the patch panels. For example, if we want to connect to Amazon, they'll run the fiber jumper after their LOA has been filled out. So now we have a physical link between those patch panels, but we still need to configure the routers. And we'll normally agree on a date and a time to configure the connection. And then once those configurations are in place, then traffic will actually start flowing between those networks. So like I mentioned on the last slide, if you're smart about where you build to, you can peer with a large number of companies with the same hardware in that same location. So this MSO or whatever company it is, let's say they have 2 routers, all these peers exist, they're going to connect to all those companies and get that traffic directly between the networks. So one thing I haven't really mentioned yet is the Border Gateway Protocol, or BGP. BGP is actually the routing protocol that makes the internet work. So you may or may not have heard of BGP, but I'm going to kind of go over, give you a little high level of how it works. If you do want to learn more about BGP and you need something to help put you to sleep, there is an RFC 4271 which outlines BGP. I mean, it'll actually tell you exactly how it works. And this is actually, these RFCs are what the vendors use to enable these features and protocols on their routers. They follow the RFC and then they write a bunch of code to get it to work on their hardware. So once you have those physical links between the routers and the network, you have to use BGP to exchange IP addresses and actually pass traffic. So here again, I am showing Cox, which, like I said, was AS22773. So let's say we connect to Telia, Netflix, and Akamai in the same data center. So each of these black lines could be a single physical link or multiple physical links. For example, this top link to Telia might be a single 100 gig. It could be 1,200 gigs that are logically bundled together. It's just shown here as a single link, but more than likely these are multiple links that are bundled. We are starting to move from 100 gigs to 400 gigs. Haven't really seen a big demand out yet in the peering world, but 400 gig is coming. So these links will start getting upgraded over the next few years. So across that physical link, we establish a BGP neighbor connection or peer. Companies may choose to BGP peer from one of their routers to one router from the other company, like I'm showing here for Telia or Netflix. Or if both companies have multiple routers, they might decide to establish two or more separate BGP neighbors for redundancy reasons. So here I'm showing Akamai. They may have two routers. Cox has two routers. They create two of these sessions. You have a hardware failure. If you need to do a maintenance to do a code upgrade and you have to take a router down, you still have connectivity or reachability through the other router. So let's go over how IP addresses are actually propagated through the internet. So an autonomous system, or AS, announces IP blocks to their BGP peers. These announcements are typically called advertisements or route advertisements. I did include a note about these IP blocks, or some of the other words they're known as routes, prefixes, subnets. There's a lot of terms that kind of describe what I'm showing here. So I'm going to talk briefly about the size of those IP blocks. So for example, 1.1.1.0/24 actually refers to a block of 256 IP addresses. These numbers, the larger the number after this slash, the larger the block of IP addresses. So if you do a /12, for example, that's way larger. And I'm going to show that in a minute. But the larger the number here, the larger the smaller the number here, the larger the block of IPs. So in this demonstration, Cox is advertising 68.0.0.12 to our BGP peers. That single /12 is actually around 1 million IP addresses. And a company, a large operator like Cox, Comcast, Charter, has many large IP blocks like this, not just one. I mean, there could be 500 or 1,000 of these large IP announcements. So this /12 is advertised to both our peers, like Netflix, as well as our upstream transit providers, like in this case, Telia. The tier 1 transit providers like Telia will actually send that IP advertisement out to all the other tier 1 providers. Because remember I showed they all connect to each other. So Telia sends it to AT&T, Level 3, Cogent, GTT to create that global internet. And here I'm just showing a picture of Europe, just really to represent it's the rest of the world. So you'll notice that Netflix doesn't send that /12 to the rest of the world. So peers only advertise IP addresses that they own to others that they peer with. They don't advertise IP addresses that they don't own to the rest of the world. So here we send that 68.0.0.12 to Netflix. Netflix does not send it to their upstream transit. So really, this is just for them to know how to reach the Cox network. So in this example, I'm showing how Netflix would advertise their IP addresses. So there are a couple new concepts to note on this slide. So the first is a concept of a more specific route or advertisement. So you can see that Netflix is advertising a /24 to Cox. /24 again is a block of 256 IPs. They are also advertising a /17 upstream to whoever their transit providers are. That /17 is a block of around 32,000 IPs. So you'll notice the first two parts of the IP or octets are the same, 44.57. That /17 contains, not only does it contain this /24, but it also has thousands of other IP addresses that they aren't advertising to Cox. /17 actually contains 128 /24s. I'm not really going to get into IP subnetting. If you ever do like a study for a CCNA, the Cisco certification, you can learn all about IP subnetting and how these IP address blocks are actually split up. It's pretty interesting if you want to learn more about that. So a more specific advertisement is preferred over an aggregate or a larger one. So in this example, when a Cox customer is watching Netflix, we know that that content will stream directly over this connection from Netflix instead of coming through Telia, because this /24 is more specific or more granular than this /17. So another term you'll hear is aggregates. So a large block of IPs that gets advertised to the global internet, like the /17 from Netflix or the /12 from Cox that I showed, those are known as aggregates. So Netflix is sending a /17 aggregate to their transit provider and a more specific to Cox. So one last thing I want to show in this example. So that /17 is sent by Netflix to their upstream transit provider, and that's tier 1 sends it to all other tier 1s. So you can see that that /17 also gets advertised to Telia, and then Telia, because they are the transit provider for Cox, or one of them. Sorry, I should have said Aurelian and Telia are the same company. They actually changed their name recently. I didn't have this slide updated. But Telia, or Aurelian in this case, advertises that Netflix route to Cox because they're sending us the global internet. So in this example, I'm just showing the rest of the internet. Just say everything. So earlier I gave the example of a Cox customer trying to reach a website hosted in Brazil. Whichever company hosts that website will advertise their IPs to their upstream transit provider. That provider will advertise it out to all the other tier 1s, in this case Telia, and then Telia will actually send information on how to reach those IP addresses to Cox. That global table of IP addresses also gets advertised to Netflix as well, but you can see Netflix doesn't send that to Cox. The peers like Netflix only send the IP addresses that they own to their peers. So here are all those examples on a single slide. I know this is pretty busy. I'm also showing an example of the global routing table, or BGP table. So this is a simplified version of that global routing table, but this global routing table can be seen on any router that is BGP peering or running BGP within that network. So I'm only showing a few lines of the table here, but this table is huge. It's actually 970,000. I just checked yesterday. That's how many entries are actually in this global routing table. And I'm actually I'll show you something like that coming up in a bit too. So the very first line in the global routing table, and this is in everyone's global routing table, is going to be 1.0.0.0/24. This is the lowest numbered IP address block there is. In this case, it is a /24. The AS path column, or autonomous system path column, shows how this router is actually learning about that advertisement. So you can think of the AS path as turn-by-turn directions. So the source is on the far right side, and the final AS who advertises it to, in this case, this Cox router, is the AS on the left. So in this case, that /24 is originated or owned by AS 13335, which happens to be a company called Cloudflare, which you may or may not have heard. So Cloudflare advertised that IP route to AS 1299, and you can see here Telia or Aurelian is AS 1299. And then 1299 is the last one in that AS path, which means Telia is the one that sent that information to Cox. So this really shows you what path each of those routes take. So now let's look at those Netflix advertisements. So if we look at that /24, this one right here, you see that AS 2906 is the only AS listed in the AS path. That's this one down here. That means that Netflix is advertising that /24 directly to Cox, because there are no other ASs listed in this path. Now let's look at that /17 that we were talking about. So in the global routing table, here is that /17. You can see that it starts at 2906, which is Netflix. Then it goes through AS, or gets advertised to AS 3356, which happens to be level 3. Level 3 advertises it to 1299, which is Telia. And then because that is the last one in this path, that's how we know that Telia advertised it to Cox. So I mentioned that more specifics are preferred over aggregates. As long as our BGP sessions to Netflix are up, we know that any streaming video to, in this case, Cox customers from that IP block will come directly from Netflix. So a question you may ask, what if these links to Netflix actually go down for some reason? And that is where those aggregate advertisements come in. So the /24 will disappear from the global routing table. This will be gone from the global routing table from the Cox perspective. But that /24, like I had mentioned, is still included in this /17. So in that case, a customer on the Cox network can still watch Netflix. There's still reachability, but those packets are actually going to come through basically Netflix, level 3, Telia, and Cox. It sounds like one thing I also want to point out, that sounds like it would add a lot of latency or a delay, lag, whatever you want to call it. But like I pointed out in the data center slide, these companies are probably all coexisted in the same data centers anyway. So even though it's going from a Netflix network to a level 3 network to a Telia, it's a pretty good possibility they're all in the same data centers, and they're literally just connecting between routers in that same site. All right, so I want to go over just some helpful tools and resources that are out there. These really help you visualize what I was referring to with BGP and how companies look on the internet. So I'm just going to kind of step through these, and I'll show you some things you can see in these tools. So this first one is called CIDR Report. This is a really good site if you do want to see that global BGP table size. You can also see statistics for each individual BGP AS. So on this status summary, this is where I got, here, I'll make this a little bit bigger. This is where I got that 970,000. So this site actually tracks the global routing table size and tracks it over time. You can also see information on individual autonomous systems. So I'm going to go click on, Cox's 22773, like I mentioned. So you can see who upstream transit providers are, and then you can see downstream or adjacent ASs. These are all companies that Cox actually sells BGP connectivity to. And this is nothing proprietary here. Anyone that knows how to look up stuff about BGP, this is published all over. You could also actually, let's go look at. Well, I'll show this up here. This is a really interesting graphic. This is showing the global routing table size over time, all the way back to 2002. So in 2002, there were a little over 100,000 IPs that were advertised in the global internet. You can see how that has steadily increased ever since 2002. The early days of the internet to now, it is, like I mentioned, 970,000. So approaching 1 million. These are just IPv4 addresses. So there's actually IPv6 BGP table as well. That one currently has 209,000. This number will continue to go up. When we first started tracking and deploying IPv6 years and years ago, this was about 20,000. It's now at 209,000. I don't think it's growing as fast as everyone thought it was going to, but this number will continually rise. All right, go back to, this one is AS rank. This is a ranking of all BGP ASs by size and reachability. So no surprise that the largest ASs are those tier ones I mentioned. So level 3, Aurelian, Cogent, NT&T. These have the largest amount of connectivity, and it's referred to as cone size, just how many BGP ASs and companies you can reach through these networks. A couple interesting things here. So I showed, Cox's AS 22773. We used to have many other ASs that were used, but now all of our, our whole network really is under one AS. And you can go and, you can see information, kind of the same information that CIDR report shows. You can show who the upstream providers are, like I mentioned, 1299, Telia/Aurelian, GTT, all of those customers we provide connectivity for. But I'll show you Comcast and Charter, actually, they have a slightly different BGP design in their networks, where they actually have an AS in different regions and markets. So Comcast has a huge number of ASs, their largest one being this 7922, and Charter is the same. Charter, partly due to company acquisitions, Time Warner and Bright House and others, Charter actually has a very large number of ASs as well. All right, so this RipeStat BG Play. So this actually lets you visualize changes in BGP routes associated with an IP prefix or BGP AS. But there's a really cool visual on this one, which I'll show you. So I'm going to look up that route that I was talking about. What was it actually? Sorry, let me go back. 68.0.0.0/12. And I'm going to zoom in here. So here is AS22773, which is Cox. You can see here is 1299, that is Telia. But it's a really cool visual to show how all these other BGP ASs are all interconnected. Almost all of these are learning of that Cox prefix through Aurelian. This other one, 3257, is GTT. You can look at a specific AS, let's say this. It's not coming up for some reason. This is just a cool visual. There are some other sites out there that'll show. It's crazy to see how interconnected all these ASs are. This site is actually really useful for troubleshooting BGP issues and advertisements. So you can look over time as routes are advertised to peers. Sometimes routes are withdrawn. Maybe a network goes offline due to maybe it's an outage or misconfiguration. This is a really good way to actually go and visualize those changes. And then the last one I want to show, so Hurricane Electric, they have a really cool 3D visual that shows, not only the data centers, but also subsea fibers. This is a really cool graphic. I'm going to turn off all these blue lines. This is showing their backbone circuits. So all these dots you see in North America just kind of represent some of the larger data centers in some of the bigger cities. So if we go look at, this is Georgia, this is Atlanta area, for example. All these large data centers exist just in Atlanta. All of these lines you see represent all the subsea fibers that go between the continents. So I don't know if you've ever seen a visual like this, but there are a lot of different subsea fibers that go from North America to Europe, for example, North America to South America, North America to Asia. It's pretty mind-blowing just looking at all this connectivity that exists. But without this, the internet would not exist. I mean, these connections are needed to get between continents, and without these, North America would only be able to access content hosted in North America.
Jason, who maintains this?
This tool or these fibers?
The fibers.
Let me change the color on. Another cool thing you can do with this map, I mean, you can go change the colors and stuff on here. Yeah, these are kind of hard to read, but there are companies that go and construct these.
Okay.
This is Japan US Cable Network, Asia America Gateway, Southern Cross. I actually know some people from Southern Cross Cable Network. I think they're based out of New Zealand. There are companies that literally have these huge ships, and they go lay these fibers, and then they lease fibers to companies. Like I don't know if you had heard of Meta, Facebook, for example.
Yep.
I think they're laying their own subsea fiber, but they actually, large enough companies that have a lot of content like that, it makes the most sense for them to lease their own fiber, or if they get to the point they go construct their own or lay their own subsea fiber versus paying, for circuits or connectivity from some other companies.
Hmm.
You know, this, I hadn't really thought of it before, but maybe we can have a subsea, I know a couple of subsea experts out in the industry. Maybe we can have a separate session just on subsea fibers. This is really interesting stuff. All right, I think that was my last slide. So let's see if any questions popped in. So Jim, I see your question about examples shown are all IPv4. Is it safe to assume that these links are now IPv6? Yes. When we establish, you know, not just Cox, but other MSOs, when we establish these BGP relationships, we do both IPv4 and IPv6. While Thuy's getting ready, I'm going to read a quick bio to get set up for him. So Thuy leads Intel's global cable segment. He joined Intel 6 years ago to support the cable access network transformation opportunity. Thuy started his career at Rogers in 1993 and has worked in cable broadband since launching the first commercial cable modem market in 1995, which was actually before DOCSIS was created. Thuy has worked for MSOs as well as cable ecosystem vendors during his career. So Thuy, you ready to go?
All right. Well, good morning. My apologies for the little bit of hiccup there at the start of this call. My name is Thuy Nguyen. As Jason mentioned, I've worked in the cable industry for 30 years now, and I started working in cable modem technology prior to the DOCSIS spec coming out in 1998. First cable modem market in a city called Newmarket in Ontario, Canada, just north of Toronto. Opportunity to work in 1995.
Hey Thuy, maybe turn your video off. That might help.
Oh boy, is my audio not working so well?
Yeah, just cutting in and out a little bit.
Can you still hear me, Jason?
Yes.
Okay. Yeah, I'm just going to turn off my webcam. Hopefully that conserves upstream bandwidth and doesn't cause. We wanted to see about running the CMTS workload that up to date has been run on a very specific appliance where you're either buying it from Eris or from Cisco or from Casa. It's a vertically integrated box that delivers the DOCSIS pipeline with very specific software and fixed function compute and I/O capabilities inside of it. Intel, with the help of virtualization technologies and our partners Comcast and Harmonic, was able to then explore how do we run the DOCSIS workload in software powered by x86 CPUs. So that's when I joined Intel to help pursue this opportunity. So is everyone still able to hear me?
Yeah, it's cutting in and out occasionally.
How's that? Is that any better?
Yeah, I can hear you.
Okay, good. I've turned off Outlook and hopefully any other resource intensive applications on my computer. Okay, so let's jump into my presentation today. I appreciate it. So this is something I wanted to share with this audience. This is a timeline of what I've just compiled. Or run all of these applications and user experiences in IP across broadband networks is really changing how we learn, educate ourselves, communicate, and our daily lives. So, in 1995, our phones were, these things that you had a rotary dial and it's connected to an MDF board and a telco, ESS5 switch or something like that, right? So you can imagine the switch here, the specialty hardware is about as big as a house, really. And we've now progressed to, being able to do the same thing that used to be the size of a house in a server that is probably 1.5 inches high, powered by software. And you can also see that much of what we do today is IP based delivery, gaming, music, everything that you can do on a phone today is delivered via software, right? We might call these things a phone, but they're not really a phone. It's just a common compute platform that runs applications. And if you really think about it, a smartphone has replaced all of. Oh man, I'm getting notifications and some echoes. Everything coming through okay still?
For the most part. Do you want to maybe take 5 and maybe, I don't know if it's your home internet or just PC? Want to take 5 and reboot?
Is there a way for me to call in on my 5G phone? Does anyone?
Yeah, there is. There's a call in.
Yeah, my apologies. Maybe my audio is just clipping too badly, and I don't want to have everyone have to validate for me if I'm coming through. Let me click the phone call. Hello?
Yep, I can hear you.
Okay, I'm hoping that this works better. I'm using my phone.
All right.
Can you still see my presentation?
Yep, still see it.
Excellent. Okay, my apologies for my broadband connection not being so great. So let me just go back to this slide. Hopefully you heard of a little bit of what I said. I drew this up just to think through, all the things that have become IP or all the services that we enjoy every day in our daily lives that have changed over the past 2 decades. Now it's unfortunately 3 decades. A phone, used to take an entire, 5 ESS switch to be able to make phone calls, and we've shrunk that form factor to being software delivered by, an x86 compute server that is around 1.5 inches high and probably, 19 inches wide, and depending on your depth, that fits in a rack. And it's powered by software, right? And a lot of what we do today in terms of TV viewing, music, audio consumption, gaming, communications with others, everything is done in IP. And I think all of you are helping your customers be able to do that and do that in a way that is reliable and a fantastic user experience. Now, if you really think about it, and what I'm illustrating here is that the device that we call a phone really isn't a phone. It's just a piece of compute, and you've got applications that run on that platform. And what it's done in the past 15, 20 years is that it's replaced all these devices we used to buy separately, right? You can do all of the things that you used to do having to buy all of these separate pieces of hardware. And then in the back end, your user experience might be a smartphone on the CPE side. In the back end, you've got a server, right, that runs software, and that server hasn't changed form factor in the telco and communication space and cable broadband space in more than 25 years. It's still a pizza box, whether it's a 2U box or a 1U box. It's still the same. It's a rack-mounted form factor. So that's maybe progress, or miniaturization is that process. So again, whether you're getting your broadband connection wirelessly or wired, in a fixed connection to your home or a cellular connection when you're out and about, these data centers that power that user experience is, back in a facility that has, power, cooling, and fiber connectivity that, are provided by, the likes of this comm service providers, such as your MNOs on the left side and your fixed providers on the right side. And that's where you get your content, right? You go to the cloud to get your content from these trillion-dollar companies that exist today. I'll pause for any questions before I move on. Can everyone still hear me okay?
Yep, audio's good now. I don't see any questions at the moment.
Great, and the slides are still coming through okay?
Yep, all good.
Great, thank you for that. So let me just take a minute and talk about what I've observed in my 25 plus years doing cable broadband. The bottom swim lane shows the timeline, and I'm looking even 10 years down the road. The DOCSIS spec is a gift that continues to give, right? It's been fantastic, and the cable industry has benefited huge from the DOCSIS spec. We've seen the standards, starting in 1997 with DOCSIS 1 to today of DOCSIS 4. But I want to draw attention to the two swim lanes above, right? The services that you're able to offer over IP is continuously evolving, and it's growing, right? I remember when we started DOCSIS, well, prior to DOCSIS, we were delivering 500 megabit per second downstream, and there was no content that could consume that. And then, DOCSIS came along, and we were offering 1.5 megabits per second, and the world was crazy about that. We could now send pictures as attachments in email because you couldn't do that before. And that spurned innovation from application providers. And I remember in 1999 and 2000, Napster came out, and people were able to share. Maybe not great for the recording industry, but people were able to share 4 or 5 minute audio clips and using peer-to-peer protocols. So I think the bandwidth capability enabled innovation of the applications that came with it. So the services in the middle swim lane shows the services that are today delivered by cable MSOs, right? And then what I want to draw attention to on the top layer is the MSO skill sets, right? The people, the human capital that has been invested to be able to deliver these capabilities and these user experiences for your consumers. First we were RF and broadcast TV experts, and that's what we did, and did it really well. In the late 90s, we became TCP/IP and routing and switching experts to be able to deliver IP signals on the internet. And then when a company called At Home Network stopped doing the email and web and DNS services, the cable companies invested in skills and resources to be able to become Linux and Unix admins and operate applications provided by the app providers. And And then into, the 2000 era, the new millennia, we became software houses, right? We became, software development shops and, DevOps and continuous improvement, continuous development environments. And then a decade later, software-defined networking and network function virtualization makes it possible to run a lot of these apps on x86 compute. Now I'm going to draw your attention to the next box, which is container networking. Right, this is the journey where you're no longer using fixed function appliances, and that's in flight right now. It's happening faster in some places than others, but you're moving from a router that is a cable broadband router that's 14 RU, consuming roughly 8 kilowatts of power, and you're moving that capability to a server or a cluster of a few servers that take up, much less space, much less power, and you're still able to deliver, approximately 200 gigabits of throughput, of DOCSIS throughput per, let's call it a cluster of, 6 or 7 RUs in a rack. Sorry about that. So, this timeline, I wanted to highlight that, the services are many and continuing to wow customers. And in order to do that, you've got a skill set that has evolved over the past 30 years to get us there. And what does the future hold, right? The future probably has a lot of AI and automation capabilities, and maybe DOCSIS 4.0 that'll take us all the way to 4 gigahertz of spectrum to be able to deliver these kinds of experiences that wow the end users and help protect the revenue of the cable broadband monthly revenue. So, let me turn my attention and your attention, to transformation. So why bother network transformation? Why transform your network? A mentor and previous manager of mine once, used the term 4 C's, right? Everything we do, we pay attention to the 4 C's. So the first C is your customer, right? How do we continue to excite our customers? We shouldn't do anything unless there's, a customer benefit. Of course, there's cost, right? There's this cost reduction to reduce OpEx and CapEx and contractual. So there's a lot of today government mandates to reduce carbon footprint, and energy conservation is a big priority for, pretty much every comm service provider and MSO that I've spoken with globally. And then of course, competition, right? How do you defend and grow your revenue, protect your revenue from your competition? And as such, much of what we do is very much dependent on the skill set that enables us to be able to do this, transformation. And let me now turn your attention to Intel as a partner, right? Can Intel help you as, you're all networking companies today, and is Intel a networking company? Now, fortunately, I'm going to, quickly flash this slide up that shows Intel powers some of the largest networks in the world today. I don't know if you all know that. I've put a few names up here. I'm sure I'm missing a whole lot, but I just wanted to highlight a few of the big, networks that we power. And we pride ourselves on building ecosystems at Intel, right? We have to innovate at least 2 years ahead of when you deploy the technologies that we've, developed. And in order to do so, not only do we develop the silicon needed to go into these, appliances, platforms, we develop the silicon as well as the software, and then we have to make it available to the ecosystem. Right? We work with your independent software vendors to get them to, integrate their software, and then we work with OEMs like Dell and HP and Cisco and Lenovo to get them to design on, the platform. And potentially we work with, systems integrators that you prefer to be able to adopt the technologies, and perhaps you'll use an operating system vendor like Red Hat or VMware to orchestrate what you need to get done on this platform. So Yeah, this is just a quick slide just to show that Intel powers pretty much all the networks around the world, and it's not just about the data center services that are in billing and OSS BSS applications.
Hey, Thuy, I have a question on that slide. So obviously
Yeah.
the cable operators, we're looking at vCMTS, virtualizing the CMTS, but seeing Verizon, AT&T, and some of them, are they doing similar things on the DSL front, or is it just like PON related, or what are you seeing? I'm curious from the telco operators.
The telcos are definitely on that journey. As you know, a lot of the telcos own mobile networks as well, right? So I think they've started that journey over 10 years ago with their mobile offerings, right? Like 3G, 4G, and 5G are really just broadband platforms, right? They've virtualized and they are now on the containerization platforms, right? The DSL networks are a little bit more complex because the access layer for DSL is pretty entrenched in legacy technologies. The DSLAMs and the various BNG technologies are on the journey to be virtualized, but it's not happening as fast as the RAN or the mobile core networks. So to answer your question, yes, the telcos are doing the same thing that the cable companies are embarking upon now to virtualize the access networks. Yeah.
All right, thanks.
So just going back about 10, 12 years, right? Intel created what we call DPDK. It's called Data Packet Developer Kit. The software that Intel innovated, we gave to the open source community and was adopted by the Linux Foundation. And the Linux Foundation was then able to help us scale it across the globe. And application vendors, application developers would develop applications that do networking workloads, can use the same server you'd buy to run your email or your CDN or your DNS or your billing applications, can be used to power data packet processing applications. So Jason, to answer your question from earlier, right, 2020, 50% of mobile core networks had already been virtualized, and by now market forecasts, like this one is from Deloro, is indicating that more than 90% of mobile core networks have been virtualized and run on x86 compute delivery platforms. So it's been going on for 10, 12 years, and part of the reason why it's been made possible is because of this DPDK developer kit. And that's something Intel created back in 2010, and we gave it to the industry as a piece of open source software. When you think of Intel as a networking company, right, there are many places in the network that you typically run Intel solutions, and you may not know that. But there's data center, the core networks, and at the edge. Here I'm depicting a base station or an antenna location. In the cable world, that edge would, in my opinion, be at your head ends, and we're working to push that edge even further because cable has a strategic advantage of having power, fiber connectivity all the way deep into your nodes, right? Your node locations. And at those node locations, you're serving a much smaller population, maybe 300 homes or 400 homes, and that in itself is a great location to be able to address some of these applications that are highly latency sensitive, as well as very strategic, because I certainly know that network providers like AWS or Google Cloud and Azure would love to have that footprint on your networks. So some of these solutions, depending on your applications, you may need, lower power CPUs or, more dense CPUs. And then, of course, heating and cooling to be able to dissipate the heat is another consideration. And I've had, the opportunity to work with Cable Labs over the past 4 or 5 years to help define the GAP spec. Right? GAP stands for Generic Access Platform, where, Cable Labs define the standard for connectivity and thermal and heat dissipation standards to be able to put a node form factor into play. And Intel participated because we want to help build a compute capability inside of these clamshell nodes, where, today you've got 160 watts of power, but we've been told that you could potentially cool up to 200 watts. So we'd like to potentially innovate in the coming, 5-6 years to put a compute and a high-speed backplane into these devices. And, maybe you'll be able to do CDN caching or, other applications for enterprise networks very deep into the network at the far edge. So just real quick, right? Intel is more than just a silicon company, right? If you think of silicon company, you think of all these gray, layers of this stack. This is what, a typical silicon company does for you. But the blue bars are where Intel will go above and beyond being a silicon provider. Most important, like I'll use me as an example. I'm not a silicon person. I'm not a, hardware, expert. I joined Intel because I have expertise in this cable market. I can help understand the requirements and ingest the requirements of the cable market. So we understand DOCSIS, right? We learned to become experts in the DOCSIS pipeline. We've recreated the pipeline in our software so that we can deliver it and deliver it well using x86 compute in our Xeons that we produce in our silicon development shop. So let's move quickly to network transformation, which is what, I hope all of you are already on this journey. I'm sharing a slide with Comcast permission. This is when we first started. I took these pictures at a head end in Atlanta where Comcast first started some of their early vCMTS deployments. This is a rack, comparison where, when you went DAA, you had the opportunity to eliminate, 4 racks of cable combining equipment in one rack that you would typically put, a CMTS and all the optical coupling equipment. So a CMTS typically is 5 racks, right? You got the, the rack of the CMTS and all the patch panels and optical equipment. And then you got about 4 racks of cable combining equipment because you were pulling the RF signal across optical lines and remuxing it in the head end. So those 4 racks are no longer needed when you went to RPDs, right? You left the RF signal out in the field and you're pulling, Ethernet across to your virtual CMTS. And so here is where, Elad Nafshi, shared with us that they reduced 20 racks into a single rack to be able to do, vCMTS. And the DAA allowed you to leave all that RF combining equipment outside and not need to pull that back into the head end. And then, these 3 fixed function appliances, all of you are very familiar with, right? It's either an Aris, a Cisco CBR8, or a, Casa C100 CMTS. And these devices, as I mentioned, are probably 14 RU in a rack. They're probably, able to deliver around 200 gigabits of throughput for your customers. And they consume roughly 8 kilowatts, sometimes lower, sometimes more, depending on how many line cards you've got activated. When you compare that to a virtual system where, you've got a leaf switch and a spine switch and a few servers, you're able to deliver 200 gigabits per second in really one server. If you add in redundancy and other, considerations for high availability, you might build a cluster of 3 servers. So you're able to do that in much less space using a whole lot less power. Instead of 8,000 watts, you're probably talking around 2,400 watts or less. So I'm taking a quote from David Watson of Comcast here. He's very proud of the vCMTS transformation at Comcast. I heard Elad speak in March in Denver, where he said that more than half of their network is now serviced by vCMTS. So more than half of the cable modem subscribers are served by vCMTS, and we're thrilled that Comcast is moving at that rate. And the benefits for this virtualization is that they're spending less on capital, spending less in OpEx, consumes much less space in the head ends, and the power that you use to power these things also come with the power that you save in the cooling of these devices. So what's more is Elad shared last month that the increased compute and the real-time telemetry that comes with all of this virtualization is allowing Comcast to resolve outages before they happen, proactively notify, and they can see much more fidelity in the network. They can see more real-time richness in the data and respond to service impairments before they become outages, and they notify customers soon after they detect them, and they're able to reduce the mean time to identify and the mean time to restore of outages by factors of 10 times faster than what they did previously on a legacy platform. So let me quickly jump into, this is what I mentioned earlier, that we recreated the DOCSIS pipeline at Intel so that we can speak authoritatively on what is needed to be able to deliver DOCSIS using software, using compute that we build, and of course the DPDK libraries, right? We've built DPDK libraries that we share with the industry so that your ISVs and the cable industry can benefit from that. So this is the DOCSIS pipeline, and we've broken it down so that we can deliver it quickly in efficient manner using x86 compute. If anyone's interested, you're welcome to go check it out and download it for yourself, because we've open sourced it. And all of you have heard of Moore's Law, I'm sure, right? Moore's Law at work is being shown here on the slide that I presented in 2022, just as an example, right? We're trying to, on every generation of new CPU, and we release a new CPU once every 12 months. For each generation of CPU we release, we're expected to deliver more performance, and most of all, more performance with less power, right? We make a promise to the industry, and I think, Gordon Moore said this, is that, there's a doubling of the amount of transistors you can fit on a piece of silicon every 2 years. And as such, we're able to add more instructions per cycle. So we call them IPC. IPC gains on every generation help to give you more performance, right? So if you look at this chart, when you go right to left with these bars, right, we went from 90 gigabits per second on one CPU 3 generations ago to 125 gigabits per second, and then 144 gigabits per second on our current generation CPUs. And along the way, we're also reducing the amount of power you need to deliver throughput, right? So it went from roughly 650 megabits per watt to 800 megabits per watt to nearly a gig per watt. And today we're above a gig per watt, right? So that's Moore's Law at work. And this is why cable and other comm service providers are moving to CPU-based delivery, because Moore's Law is doing the work for you, not having to do anything. So let me turn quickly to what's ahead for DOCSIS 4.0. I've taken a few screenshots here. This is Matt Peterson from Charter showing that DOCSIS 4.0 tests in their lab show that they could deliver 8.9 gigabits per second downstream and 6.1 gigabits per second upstream. That's fantastic. I think we're now in the realm of PON speeds, right? Multi-gigabit broadband that I showed earlier. And then this is Comcast, Rob Howell, showing similar at the same event, where Comcast showed that with FDX, which is 1.2 gigahertz in spectrum, is showing 8.2 gigabits per second downstream and 5.1 gigabits per second upstream. And Comcast will start rolling that out in commercial deployment, I'm told, later this year, and they'll ramp that up next year. And then here's our European, tier one operator, Liberty Global, showing that they produce, 8.5 gigabits per second downstream and 6.4 gigabits per second upstream. So these are exciting, spectrum and, DOCSIS modulation and DOCSIS protocol and advancements. Now the hardware has to be able to deliver that for you. And, we're delighted to be part of this process, and we're innovating to be able to deliver these results for you in a cost-effective manner. So, I think next-gen DOCSIS gives MSOs a lot of options. And I've just taken this chart from a white paper that Karthik Sundaresan wrote a couple of years back. And with all these spectrum options available to you, whether it's extended spectrum DOCSIS or full duplex DOCSIS, MSOs have the ability to deliver various combinations that fit your customers' needs. We've heard that some may be even considering more than 10 gigabits per second downstream. If they don't think that customers want or need 6 gigabits per second upstream, they'll use some of that spectrum for the downstream. So maybe they'll cap the upstream at 3 gigs and use more of that spectrum for the downstream. On today is limited by 8.6, but cable will probably be able to deliver more than 10 gigabits per second easily. And in our testing, we've shown that we can do more than 10 gigs on a downstream using x86 CPU cores. So really, at the end of the day, you've got a lot of options, and hardware isn't the limiting factor. Back in the days when I worked in the MSO community, for an MSO, we typically had to figure, what we'd need, and the hardware was very specific to that task. Not so in the, virtualized world, containerized world, where, now you've got software-defined networking and container networking, allowing you a lot of flexibility, right? So the same server, the same hardware, and the same Ethernet, cards that you typically use for DNS or email or video transcoding can also be used for virtual CMTS or doing routing and other functions that you typically do in your data centers with billing and provisioning and network management. So first pick the CPU that you think you're going to need and determine whether you're worried about rack density and blast radius or not, number of customers you want to place at risk on the same server, on the same power supply, and then figure out, how much IO do you want to put out there. Is it, 100 or 200 or even future 400 gigs of IO throughput? And then that helps you with your server sizing. And then, of course, your rack, if you've got power limitations or, blast radius considerations. So the hardware is the same. It's very flexible, very robust. That allows you to deliver DOCSIS 4.0 speeds. So I'll pause there. That's pretty much my presentation for the day, and I really appreciate the opportunity to be here. I hope my audio has been coming through better in the past 40 minutes.
Thanks, Thuy. Yeah, audio's been good. I do have a question. One of the earlier slides, I know you had DOCSIS 5.0 listed there. I think we know 4.0 is, probably still a year or two out from deployments, and that's probably a 5, 6, 7 year deployment cycle for MSOs. Do you think DOCSIS 5.0 will materialize?
I'm pretty sure, based on what I heard, that it will. In the conference I was at in March, I'm told that some are already starting to write the spec to be able to get the spectrum up to 4 gigahertz, right? So today, DOCSIS 4 is at 1.8 gigahertz of spectrum, and I think 16K QAM. You know, DOCSIS 5 is very real in my opinion. I think it'll happen in the next decade. So I know that many MSOs are, particularly the MSOs I speak to in Europe and in Latin America, you know, they have different economic conditions, and they believe they want to move to PON as their end game. And I think even in North America, you know, PON will probably end up being the end game, but the economics has to be able to make it work. If you're going to trench to customers' home, as I understand it, in the North American market, the cost is still around $700 to trench fiber to a home. Why trench if you can deliver 10 gigabits per second to a home using an RF coax last mile with DOCSIS 4.0? So I just think it's a possibility that you have at your disposal, right? The cable industry has great tools. This DOCSIS spec has been phenomenal. So in my opinion, I'll probably be retired by then. DOCSIS 5 will come in, you know, probably, you know, the spec should probably be written in about 5 years' time.
Thanks. Yeah, I agree with that. I think a lot of companies that have looked at doing more fiber to the home just realized obviously how expensive it is for that physical construction. And the fiber itself's not pricey, but just getting it to the house, just like you said. So if we already have that cable plant there and we can continue to evolve it to increase these speeds, then economically it's the most viable for sure.
Absolutely. And, you know, I've talked to some operators in Europe where, you know, they'll run fiber to the building, like an MDU building, but inside the building, they have coax, right? So you're just going to use coax to get into the customer's apartments, right? There's no point in ripping that coax out and putting fiber in if you've already got the ability to run coax. That's an expensive proposition as well.
Yep. All right. I don't see any other questions. Does anyone have any questions they want to come off mute and ask?
Yeah, well, feel free to send chat.
All right. Thanks a lot, Thuy. That was great.
Absolutely. And, you know, I want to thank again the local chapter for having me. And, you know, container networking is something that I'm sure all of you are looking at. And if there's, you know, any questions I can offer answers for, you know, that realm, be happy to do it. You know, Kubernetes, Docker, container, all these things are probably fairly new to MSOs. And when I've spoken with executives of MSOs around the globe, you mentioned that it's not something that you have a lot of people with those skills. But I think there's a lot of benefit that MSOs will gain by going to container networking. Because you know, when I worked in the cable company, we thought we were pushing the limits of scale, you know, in terms of millions of users. I you know, didn't realize a few years later that the likes of, you know, TikTok, Facebook, Instagram, and WhatsApp would be pushing that limit to billions of users, right? So in order to scale efficiently, you know, we couldn't do it with, you know, routers and switches that are, you know, in the current fixed function appliance that we had been relying on 10 years ago. So to be able to do it on hardware that, gets shipped in millions of volume a year makes it more economically viable, as well as more power efficient and space efficient. And that's possible because of software like container networking.
Yep. Cool. Well, thanks a lot.
Okay. Absolutely.
All right.
My pleasure, Jason.
All right, thanks. So we'll go ahead and close it out. We did send out a survey related to our technical training. If you have responded to it, thank you. If not, please do so. Some of the questions we're asking in there, do you like this quarterly type of format? Would you prefer maybe the same day once a month? Maybe we do an hour session. Just curious to get your feedback on that. And then also just any ideas for content or things you would like to see. One idea we were kicking around recently, with cable games coming up next week, we will probably do some sort of session specific to those events that are in the cable games. Maybe follow a month or two after the cable games. Just, maybe if people are struggling on certain things, just help get some training there to help you start prepping for the cable games next year. So that's just one idea we're thinking about, but curious to hear feedback from others. So with that, thanks again for attending, and we'll send something out once we get the next one scheduled. Thanks.